if you're talking about a stationary particle, clearly a stationary particle has only one non-zero component, right? Only the time component. Because everything is stationary, the r is not changing, nothing has changed. There's no velocity except for u0. And in fact, one can do this calculation with the geodesic equation. It's very simple. The r component of the acceleration is the covariant derivative is equal to du ds d tau of the r component of the velocity multiplied into that, because you have du d tau is equal to basically, like, or let's say the covariant derivative. You need to multiply in this thing over here. Mm-hmm. Okay? When you do this, so you're going to have just the covariant derivative of u0 over here. Okay? And when you end up, so you can see that you're going to get, what you end up getting, it's easy to see, is this. And then times this u0 and this u0, so you get u0 squared, which, if you do ds squared is equal to g00 d tau square, dt square, right? So you get g00 is equal to ds square over dt square, and this is u is dt ds or d tau, dt d tau square. This u and this u multiplied. So you just get a factor of g00. But that's for later when I deal with the metric. But it's easy to do this calculation and to see that what comes out is this gamma r00 piece. If you do the geodesic equation over here, then again, you can show by symmetry considerations for a static field. It's not, and the Earth is not spinning and so on. So it's not just stationary, it's static. That you would need maybe special relativity to talk about c and the scale factor if it's slow speeds and so on and so forth. And then you can show also in the geodesic equation that you're only going to get this gamma r00. But it's easier to show in the stationary particle. So, and this turns out this is actually a vector. So what you have is this 4 vector, which has one component, the acceleration in the radial direction, and it has the magnitude of basically gm over r squared. This gamma, that's the central, in the Newtonian regime, that's the central aspect of your acceleration. And in fact, like what I showed you in the Weinberg thing, you can see that these gammas are actually accelerations. Again, multiplied by a little piece, and that has to do with the g00, but that's afterwards. So now, if you want to have a field equation, what you want to do is, this is your field quantity in AR, as far as you're concerned, right, from Newtonian physics. So you're going to try to write some kind of a field equation in this warped space-time, where the field quantity is this AR. So what are you going to put in? Basically, this gamma. So now, what is my field equation? For various good reasons, you're going to use a differential version of the field equation. For example, the gm over r squared is really the solution of the field equation. When you say Newtonian theory, acceleration is equal to, incorporating the equivalence principle, you say acceleration is equal to gm over r squared, that's really a solution. It's not presented that way in ordinary Newtonian gravity. The field equation is, for example, divergence of A equals to rho, or in vacuum equals to 0, and then you have boundary conditions and so on. So that's what I'm going to pattern the field equation on. Instead of div A equals 0, I'm going to instead have, of course, this gamma. And this is just like a prototype. Obviously, this is just heuristic, but this is what I expect it to look something like this, at least in the Newtonian regime.